Okay. R.7. Can somebody swing that door shut for me? Properties of exponents. So the properties of exponents all follow directly from the definition of what an exponent is, which is just repeated multiplication. So a to the n power is equal to 1 times n factors of a. So the good news about all these rules is that even if you forget them, you can always kind of come up with them on your own just by doing like a simple example, because they all really do just follow from repeated multiplication. So the first two, which you've probably seen before or alluded to before at least, are the product rule and the product rule says if I multiply n factors of a by another m factors of a, well, n and m are both just counting factors. So if I have n factors of a and then I have another m factors of a, I have a total of n plus m factors of a. So for example, if I have 3 factors of x and I multiply that by another 5 factors of x, well, all that's happening here is that we're lining up a bunch of factors of x. 1, 2, 3, 4, 5. And because the operation is just all multiplication, we're just counting up a bunch of factors of x. So this is x to the 8th. Now, one thing that this relies upon is that our exponents are actually counting the same factors, right? If I have 2 to the 3rd times 3 to the 4th, well, I don't have 7 factors of anything, right? There's 3 factors of 2 and there's 4 factors of 3, but I don't have 7 factors of any one number. And so there's no way to simplify this, I mean, other than just multiplying and getting a humongous number. Because those exponents aren't counting the same factors, we can't combine those in any way. And so that just can't be simplified. So all of this is reliant on having the same base in the two exponential expressions that you're multiplying, so that your exponents are actually counting the same thing. And the same goes for the quotient rule. Which says if I divide two exponential expressions with the same base, well, then I'm just reducing the number of factors, right? If I cancel m factors of a, then I'm reducing the number of factors of a by m. So for example, if I have x to the 5th, over x squared, this is 5 factors of x over 2 factors of x. And so, of course, 2 factors cancel. And so what I'm really doing is reducing the number of factors in both the numerator and denominator by 2. So we have x to the 5 minus 2 and x to the 2 minus 2. But then in the denominator, like, we end up not having any factors of x, right? So we don't typically write that. We just write the 5 minus 2. And so that gives us x to the 3rd.
You have to write the step of x to the 5 minus 2?
No.
Okay.
this, the result of this always goes in the numerator. If you're subtracting the exponent on the bottom from the exponent on the top. So then the quotient rule leads us to a few things that we'll want to talk about. The first one is an exponent of 0. So if I have x to the 5th divided by x to the 5th, well, according to the quotient rule, that should be x to the 5 minus 5, which is x to the 0. What is x to the 5th divided by x to the 5th, though?
1.
Yeah, it has to be 1, right? Because anything divided by itself is 1. Which means that x to the 0 has to be equal to 1. And, I mean, there's a few ways to think about that. One is just as justification of our quotient rule. Another is if we think about that definition that a to the n is 1 times n factors of a, then if I have x to the 2nd, that's 1 times 2 factors of a. Oh, not a, but x. And x to the 1st is 1 times 1 factor of x. So without even thinking about it, just following the pattern, what should x to the 0 be? 1 times
0.
Which doesn't mean like 1 times the number 0. It means 1 times like no more factors. So we just end up with 1. So, and anything raised to the 0 power is 1. We have to be a little bit careful with order of operations as far as what is actually being raised to the 0 power. So if I have 4x to the 0, well, that's not going to be equal to 1 because I'm not raising the entire expression to the 0 power. This is the number 4 times the exponential expression x to the 0. So 4 times 1, which is 4. As opposed to if I had 4x as my base and I raised that to the 0 power, then that is equal to 1. So regardless of what the base is, if that whole thing is in parentheses raised to the 0 power, then that whole thing is equal to 1. How about that? What do you get? Yeah, it's -1. That negative sign, especially when working with exponents, it's really helpful to think of it as multiplication by -1 anytime you see a negative sign. And so that's -1 times 4 to the 0. So it's just an order of operations thing, right? We raise 4 to the 0 power first and then multiply by -1. So we would get -1. And so it's true that anything to the 0 power is 1. We just have to be a little bit careful about what operations are actually happening in the expression before we just immediately write a +1 every time we see a 0. So let's add this to our list. We have an exponent of 0. So a to the 0 is equal to 1. So the other thing that our quotient rule can lead to is negative exponents. For instance, if we have x squared over x to the fifth, well, our quotient rule says that this is x to the 2 minus 3, which is x, whoa, getting ahead of myself, 2 minus 5, which is x to the negative 3. But thinking about, again, that definition of what it means to be an exponent as repeated multiplication, this is also x times x over 5 factors of x. And so if we cancel our common factors, we get 1 over x to the third. So again, if our quotient rule is true and our definition of exponents is true, these two things have to be equal to one another. And if we think about the definition of exponents, 1 times n factors of x, so x to the n is 1 times n factors of x. Well, it doesn't make sense to multiply 1 times negative n factors of x, right? Like, that's impossible. You can't count a negative number of things. But if we think instead of that negative sign as like an opposite sign, we can think of this as 1, and then the opposite of multiplying by n factors of x. What's the opposite of multiplying? Dividing. So this is 1 divided by n factors of x. And so that's how we get 1 divided by x to the n. We have to be a little bit careful with this definition because the way that the rule is stated makes a lot of people feel like anytime they see a negative exponent, they have to like write a fraction with a 1 on top, which isn't actually the case. What that 1 over x to the n really means is the reciprocal of x raised to the positive n, which means that if x to the negative n was in the denominator, the reciprocal of that will be in the numerator, right? So it's really just switching. It's not that anything with a negative exponent ends up in the denominator. So if we had, say, 2/3 to the negative fifth, well, that's the reciprocal of 2/3 to the positive fifth. So we take the reciprocal of our base to the positive fifth power. So we're not necessarily just writing 1 over something. It really just means take the reciprocal of that base. So similarly, if we had 1 over x to the negative third, well, the reciprocal of that would be x to the positive third, technically over 1, but when we divide by 1, we don't need to write it, so I'll just leave it there. So it really just means, so if it was in the denominator, that the negative exponent will give us a positive exponent in the numerator, and then vice versa. So our negative exponent rule says a to the negative n equals the reciprocal of a to the positive n, also known as 1 over a to the n. Okay, and then we just have a couple more rules, and then we'll get to like how to use them to actually simplify expressions. So let's say we've got x squared to the third. So this says that I have 3 factors of x squared. So x squared times x squared times x squared. So my product rule says if I have the same base, I can add my exponents. So this is going to be x to the 2 plus 2 plus 2. But that looks like I'm just adding 2 repeatedly. What's another name for repeated addition? Yes, multiplication, thank you. So adding 2 3 times is the same as doing 3 times 2. It's actually a pretty cool relationship. The relationship between addition and multiplication is identical to the relationship between multiplication and exponents, right? Exponents are repeated multiplication, and multiplication is repeated addition. And all the rules actually have like corresponding rules for the other relationship. It's kind of cool. We'll see that in a minute when we talk about the distributive property. So this would give us x to the 6th. So if I do the product rule repeatedly, that gets me what we call the power rule. Which says that raising an exponential expression to another exponent, we can simplify by multiplying the 2 exponents. Okay, so let's look at 3 things. Let's look at 3x to the 4th. Four times x plus 3 and x plus 3 to the 4th. So 2 of these have rules that help us to do them quicker, and 1 of them does not. Anybody want to guess which is which? Okay, we'll do them. So 3x to the 4th, that is 4 factors of 3x, yeah? So 3x times 3x times 3x times 3x. So we have 4 operations, well, basic operations: multiplication, division, addition, and subtraction. How many of those operations do you see on the right side? Just 1, right? It's all multiplication. I mean, we've written it a little differently in different spots, but really this is just 3 times x times 3 times x times 3 times x times 3 times x. And because it's all 1 operation, I can use the commutative property of multiplication, which says that you can multiply in any order, right? 2 times 5 is the same as 5 times 2. And so I can move these factors around and say this is 3 times 3 times 3 times 3 times x times x times x times x. And now that I've reorganized those, this is just 3 to the 4th, and this is just x to the 4th. So I had a product inside the parentheses, and I can apply the exponent to both factors. That's what we call the power of a product rule. And that rule is entirely reliant on the fact that the exponent is repeating the operation that's already inside the parentheses, right? So when I rewrite that exponential expression as repeated multiplication, it results in me having only multiplication in that expression. So if I multiply 4 times x plus 3, we said before that multiplication is repeated addition, right? So this is the same as me adding x plus 3 plus x plus 3 plus x plus 3 plus x plus 3. How many operations are on the right side there? Is there multiplication? No. Is there division? Is there subtraction? Is there addition? So there's only one operation again, right? It's all addition. I mean, I've grouped those x plus 3's with parentheses, but they're really unnecessary because if we look to the left of each set of parentheses, there's nothing to distribute, right? So this is really the same as just x plus 3 plus x plus 3 plus x plus 3 plus x plus 3. And again, addition is commutative, so I can do it in any order I want. So I can rearrange all of those terms to get x plus x plus x plus x plus 3 plus 3 plus 3 plus 3, which is 4 times x plus 4 times 3. What property did we just demonstrate there? This one's not new. Why do you guys always whisper when you answer questions? I'm going to start whispering every time you ask me a question. What'd you say there, David? Yes, the distributive property. That's okay. Even if you were wrong, we wouldn't laugh. No, we still wouldn't laugh. Because we know that we're all wrong sometimes, too. Even in really horrible ways. That's how we learn. So the distributive property shows me how to combine multiplication and addition. And again, the reason that it works is because the operation outside the parentheses is just repeating the operation inside the parentheses, right? So multiplication is repeated addition. Up here, exponents are repeated multiplication, so the operation outside is repeating the operation inside. So we can do the same thing down here.
So your answer on that one would be 4x plus 4 times 3?
I mean, we're not really talking about answers, we're just doing math. I mean, I would never write all that out as a way to do the problem. So if I write this out as repeated multiplication, how many operations are there? There's 2, right? There's addition and there's multiplication, which means that what I did in the last 2 problems, like, won't work because I can't start just rearranging everything because I have to distribute to take care of the multiplication and the addition being combined. And so there is just no rule for this. We can't do x to the 4th and 3 to the 4th, and the reason is that the operation outside the parentheses is not repeating the operation inside the parentheses. So we have some nice handy rules like this one and this one, but we can't take those to mean that you can just distribute anything outside parentheses to things that are inside the parentheses. It's all based on how the operations are related to one another. So we can distribute exponents over multiplication, and we can distribute multiplication over addition. But beyond that, we can't just start distributing everything in sight, right? So this rule that we just saw, again, is called the power of a product rule. Which says that if you have a product raised to an exponent, that you can raise each individual factor to that exponent. And then the last rule is the power of a quotient rule. And this one's probably the easiest one to see. If you have a fraction raised to the nth power. So imagine if you line up a bunch of factors of a over b, you would just have n factors of a on the top, right? And then n factors of b on the bottom. And so this is just a to the n over b to the n. So similar to the power of a product rule, we can apply that exponent to the numerator and the denominator. So now let's talk about how to use these all together to simplify exponential expressions. So probably the trickiest part of dealing with exponential expressions is knowing when you're done or knowing where to start, right? Like what to do first and when you're actually done simplifying. So if you think about three things, let's see, simplifying, exponential expressions. There are basically three things we don't want in our final answer. The first is parentheses. So you're going to ask yourself, are there parentheses? When you ask yourself this question, don't count parentheses around negative numbers. For example, like negative 4 to the 9th times x doesn't count as having parentheses in it because those parentheses aren't grouping an operation, right? They're just grouping a number. So if there are parentheses, you will use the power rule, the power of a product rule, or the power of a quotient rule to get rid of them. The second thing you want to look out for is, do any factors have the same base? For instance, if I have x to the 3rd times x to the 5th, then those, I'm multiplying two factors that have the same base, and we can use the product rule to combine those into a single factor. So if yes, you're going to use the product rule or the quotient rule. And then the last thing we don't want in our final answer is negative exponents. And that's sort of a general thing. We typically don't like negative exponents in our final answers, mostly because they don't make much sense in terms of repeated multiplication, right? We'd rather think about dividing by x to the fifth than like multiplying -5 factors of x, because that doesn't really make much sense. There are times when you will use negative exponents in a problem as far as your process goes, but in your final simplified answer, you want to have positive exponents. So are there any exponents? If there are, then you'll use the negative exponent rule. To rewrite with positive exponents. This list is probably a good list to keep next to you when you're doing your homework, so that you don't feel like you just have to look at it and know everything to do all at once. It sort of gives you a little bit more systematic way to do it. Yes?
Is there anything special that have to be done for decimal exponents, or would we just carry the decimal over?
No, you can use the same exact rule for decimal exponents or fractional exponents, which we'll talk about tomorrow. But all the same rules apply. And we don't have to rewrite, like decimal exponents we never really rewrite because they don't have a nice translation. We'll see tomorrow rational exponents we can write as radicals. But the same exact rules apply, and we don't have to like get rid of them in any way. The order that you do these three things in doesn't really matter, because the only operation going on here is multiplication and division. They're all part of like the same step in the order of operations, and so it doesn't really matter what order you take care of these things in. It's often convenient to get rid of parentheses first, but as you do more and more of these, you'll kind of find the most efficient ways to do each individual problem. So let's simplify a couple of these guys. Let's simplify -2. Okay, so like I said, the order that you use doesn't really matter. When I look at this, I sort of see inside the parentheses that I have factors that have the same base. And so if I can simplify those first, then I have a little bit less to work with when I get rid of my parentheses. And so I'm going to take care of that x to the third divided by x to the -5th, and that y to the -2nd divided by y first, just by using my quotient rule. So the quotient rule says to subtract your exponents. So we have -2, and then the exponents on my x are 3, and then I'm subtracting an exponent of -5. So that gives me x to the 8th. And then I have y to the -2nd divided by y. Y is just y to the first. We don't write that exponent, but it's one factor of y, and so this is an exponent of -2 minus an exponent of 1 gives me an exponent of -3. So y to the -3rd. And then that whole thing is raised to the 4th power. So we took care of our factors with the same base. Now let's go ahead and take care of those parentheses. So I'm going to apply my exponent of 4 to all of the factors. There's 3 factors inside the parentheses. We have a factor of -2. If you remember nothing else that I tell you today, please remember to put negative numbers in parentheses. Not because I really like for you guys to have to make parentheses and I think it looks prettier, but because it means something differently to write this than it does to write this. Right? So the first one is a factor of -1 and 4 factors of +2. And the second one is 4 factors of -2. So if you don't use parentheses, you're mathematically saying something different. And it'll get you a different result. So every time you have a base that is a negative number, you want to put it in parentheses. And then we have x to the 8th raised to the 4th power. So our power rule says that we can multiply those exponents. So that's x to the 32nd. And then y to the -3rd to the 4th is going to be y to the -12th. And then the last thing we're going to do is take care of my negative exponent. So every time I see a negative exponent, I just draw like a fraction bar. And then I'm going to go through factor by factor. And anything that has a negative exponent will move, and anything that does not have a negative exponent will stay where it is. So -2 to the 4th has a positive exponent, which means it stays in the numerator. Because remember, this whole thing you can think of as like being over 1. And so that whole thing that we started with is like in the numerator to begin with. X to the 32nd has a positive exponent, so it stays in the numerator. And then y to the -12th has a negative exponent, and so it needs to come down to the denominator to have a positive exponent, so y to the 12th. Notice that -2 to the 4th, it has a positive exponent, so don't be tricked every time you see a negative sign to like put it down in the denominator. A negative number is just a negative number. It stays the same. What's up?
So do you want us to like simplify the -2 to the 4th power, like in the problem, or not?
I don't really care, but if you do it, like if you, some people really just have a hard time resisting, but if you, and that's okay, but if you do it as your very, very, very last step. Like at this point, you could write this as 16x to the 32nd over y to the 12th. Because trying to do it too soon you start to get like negative numbers and negative exponents mixed up, and then your signs get kind of wonky. So always as your very last step if you want to simplify that. And really, like, this one would be fine, but if the exponent's more than like 4, the numbers just get huge, so you might as well just leave it in exponential form. Okay, let's look at another one. How about so on this one, I think I want to get rid of parentheses first, because it's going to be really hard to combine those into a single fraction until I get rid of parentheses. So we are going to apply the exponent to each factor in each fraction. So I have an exponent of -5 So I have 3 to the negative 5th, a to the negative 15th, over b to the positive 25th. So negative times negative will give me a positive down there. And then over here we have a to the negative 4th to the negative 3rd, so that gives me a to the positive 12th. And then my base is negative, so it goes in parentheses and then to the negative 3rd power. So now we sort of have two choices. We can take care of the negatives, or we can combine where I have the same factor, or two factors with the same base. So I think I'll take care of that first, because I have that a to the negative 15th and a to the 20th. So we have an exponent of negative 15 and an exponent of 12 will give me an exponent of negative 3. So all one big fraction, 3 to the negative 5th, a to the negative 3rd, b to the 25th, and negative 2 to the negative 3rd. So last thing to do is take care of those negative exponents. So again, just kind of make a fraction and then go through factor by factor. So a negative exponent means that it will switch places to get a positive exponent. A positive exponent means stay put. So you want to be careful. Like a negative exponent doesn't necessarily mean it's going to end up in the bottom. Positive doesn't necessarily mean it's going to end up in the top. It's more that negative will move and positive will stay. So if I have 3 to the negative 5th, that's got a negative exponent, which means it's going to come down to the denominator with a positive exponent. So that's not an a, it's a 3. 3 to the 5th. And then I have a to the negative 3rd, which again has a negative exponent, so it's going to come down to the denominator with a positive exponent. B to the 25th has a positive exponent, so it stays where it is, which in this case is in the denominator. And then negative 2 to the negative 3rd will have has a negative exponent, so it's going to move to the numerator. And we have negative 2 to the positive 3rd. Notice that just changes the sign on the exponent because we took the reciprocal. And so again, at this point, if you really wanted to, you could call that negative 8. I don't know off the top of my head what 3 to the 5th is, so I'm not even going to do it. Like really, if you don't know what they are without your calculator, you might as well just leave them. The important thing here is manipulating the exponents. It's not so much multiplying things by themselves a bunch of times. Like I know you guys can do that. So I'm more concerned with the exponential expressions than like whatever number you get when you multiply 3 by itself 5 times. So tonight you have online homework and then a couple problems out of the book. Again, we should have your test